Hello, my name is Sarah. Today I'm going to be talking about the effect of electric field on oxygen reduction reaction kinetics, and specifically how we can use it to rationalize pH dependencies that we see on several different electrodes. So as I get started, I just want to briefly talk a little bit about 2-electron and 4-electron oxygen reduction. So if you're in this session, I'm guessing you probably know about the 4-electron oxygen reduction reaction, which is the reaction that happens at fuel cell cathodes, which takes oxygen and reduces it to produce water. And when we think about how we can kind of kinetically model this reaction, the very simplest way that people do that is by thinking of a mechanism where you basically reduce, you transfer 1 electron and proton per elementary step. So take O2, create OOH on the surface of the catalyst, then OOH to O to OH, and finally OH will then get protonated to create water. We can also think about the 2-electron oxygen reduction reaction, which produces hydrogen peroxide from oxygen. This is a less thermodynamically favorable reaction, but it's important to think about for several reasons anyway. When we think about the mechanism, we think of it having the same first step, O2 being protonated to create OOH, and then OH protonating again to become hydrogen peroxide. Now we care about this reaction for a couple reasons. The first is that when we're actually looking at a fuel cell cathode, we don't want this reaction to happen. That's because hydrogen peroxide is corrosive and it can lead to a shorter lifetime of a fuel cell cathode. However, there are certain new applications where we might want to have hydrogen peroxide produced electrocatalytically. That is because hydrogen peroxide, as it currently made, requires a large setup, a large plant, and so this would be a way to maybe make it in a more distributed way. But in other words, we need to be able to kind of understand when we can selectively produce both 4-electron and 2-electron hydrogen peroxide. So in terms of previous theoretical models as to how we can kind of understand these on a wide range of catalysts, there are a few ways we can look at it. The first is by doing a very simple limiting potential analysis. And in that way, kind of creating this kind of activity volcano where you have binding energy on the bottom to represent the binding strength of the catalyst. And you say the limiting potential is the potential at which all steps are either thermoneutral or are energetically favorable. So what you see when you create a volcano of different catalysts along this is on the left-hand side of this, where you have strong binding catalysts, you have catalysts that are limited by that final protonation step, OH to water. And on the right side, where you have weak binding catalysts, you have catalysts that are limited by creating OOH from O2, the very first step. And if we look at the red versus the blue here, what we see is it's only on these very weak binding catalysts where we have red, the 2-electron oxygen reduction reaction, that's competing with a 4-electron oxygen reduction. This can be kind of made a little bit more complicated by doing a full kinetic analysis. And when people have done that, they found very similar results where you have water at 0.9 volts, you're going to see things like platinum be close on the strong binding side, but close to being the best catalyst. And hydrogen peroxide, on the other hand, you have much weaker catalysts that are good. And specifically here, we have the 2 gold catalysts that look like they would be good hydrogen peroxide catalysts. Now, all of these methods both rely on assuming that you're always transferring protons and electrons at the same time, that they are always transferred coincidentally. And so this is kind of analogous to the experimental reversible hydrogen electrode and seeing things that are completely dependent on that reversible hydrogen electrode. But then by nature, because that they assume this proton and electron transfer happens at the same time, they can't describe pH dependence on that reversible hydrogen electrode scale. And while that's useful in some situations, we can see some places where there's limitations, and we'll go over that now. So if we look at polarization curves, these are all from experiments of these 3 different catalysts that we're talking about, platinum 111, gold 111, and gold 100. If we start just by looking at the top, this is the total current polarization curve, which for in most cases is pretty similar to just the 4-electron. If we look at platinum, what we see is that pH 1 in red and pH 13 in blue, we have almost exactly the same polarization curve versus the reversible hydrogen electrode. Then, though, if you look at gold 111 or gold 100, what we see is we see much more active, much more higher onset potential in base than we see in acid. And this happens on both electrodes. Now we can look at those same electrodes, gold 111 and gold 100, and how their current toward hydrogen peroxide, as measured by a rotating ring disc electrode, changes. And what we see, interestingly, on gold 111, what we see is that we have the same onset potential for the 2-electron down here and the 4-electron oxygen reduction reaction. And that happens in both acid and base. However, on gold 100, while in acid, in red here, we have the same onset potential for the 2-electron and 4-electron processes. In base, we see that the 4-electron process has a much higher onset potential than the 2-electron process, and it's therefore more active and a good 4-electron catalyst. So this kind of raises two main questions that we want to get to by the end of this talk. The first is, why do different electrodes have different pH dependencies? So why does platinum have a very small one while the gold surfaces have much larger ones? And the second is, why do 2-electron and 4-electron oxygen reduction have different pH dependencies on catalysts like gold 100, as shown here on the right, but not on catalysts like gold 111 or platinum 111? So in order to do this, we kind of have to think about how we can differentiate pH dependence on an AIChE scale. And one way we can think about that is things that are dependent on the SHE scale versus the AIChE scale. And since those two scales are only differing by pH, a dependence on the SHE scale would show up as a pH dependency on the AIChE scale. So we can kind of think about it when things are purely dependent on the SHE scale, we think of them as purely electronic contributions to the activity. Whereas when we think of things on the AIChE scale, we're thinking about things that are contributions that come from coupled proton and electron transfers if they happen solely dependently on the AIChE scale. So one way to really measure the SHE dependence, we know how to measure the AIChE dependence, but how to measure the SHE dependence is to look at electric fields, which is completely dependent on SHE and not on the AIChE scale. And the way we've done this here is we've used a pretty simple parallel plate capacitor model where the CH, epsilon, and PZC are all going to be constants that depend only on the electrode you're looking at. So if we look on the left here at the specific actual DFT calculations we did to try to understand what these field effects on the different adsorbates are, what we see is that all of these adsorbates have some amount of field dependence on field. Specifically, O2 and O have these kind of monotonic and decent medium to large size field effects. OOH and H2O2 have these kind of parabolic dependence on field. And the OH here in the middle really has the smallest dependence on field. And that'll be important later. So remember that there's very little dependence of OH on field. So then when we go to put this into a kinetic model, what we do is we first correct for the potential versus SHE using these field effects that we just calculated. And then we correct for the potential versus AIChE using the computational hydrogen electrode that's been described many times and was used in those two studies that I showed earlier. So how do we do when we make a kinetic model when using these principles? We can look at how our kinetic model compares to the experimental data that I already showed in order to understand this. And what we see is that our kinetic model for platinum 111 does a really good job. Our kinetic model on the left shows that we have a similar onset potential across the pH range on platinum 111. Oops. It also shows that we have much lower onset potential for 2-electron oxygen reduction than we do for 4-electron oxygen reduction in both acid and base. On gold 111, we see that our model correctly predicts that we have a much higher onset potential in base than we have in acid. It also correctly predicts that the 2-electron and 4-electron oxygen reduction reactions have the same onset potential in both acid and base. So this and this are the same. Finally, gold 100, we show that our kinetic model, which includes the effective field, once again correctly predicts that we have a higher onset potential in base than we have in acid. We also predict, as we showed in this kind of strange experimental phenomenon that happens on gold 100, that 2-electron ORR and 4-electron ORR have the same onset potential in acid, but not in base. So as you see here, these two red lines are the same, whereas this blue line is much more active than this 2-electron blue line. So I hope these last three slides have really shown you that our field effect model can pretty well predict pH dependencies that are seen in experiment on all three of these electrodes. And what we want to do here is actually try to understand why this does so well. So the kind of return to those key questions I brought up earlier. First, why do different electrodes have different pH dependencies? And second, why do the 2-electron and 4-electron ORR have different pH dependencies on some electrodes like gold 100, but not on other electrodes like gold 111 and platinum 111? And in order to do that, we're going to look at activity volcanoes. First, we're going to look at an activity volcano for the 4-electron oxygen reduction reaction at 0.9 volts versus RHE. So what I've done here is plot what the kinetic model predicts for all of these, for an activity volcano at a bunch of different fields, all at 0.9 volts versus RHE. And I've placed gold 111, gold 100, and platinum 111 on it based on where their binding energies are. And the first thing that kind of pops out is that on the strong binding side, where platinum 111 is, we see a very small field dependence, whereas on the weak binding side, where gold 100 and gold 111 are, we see a much stronger dependence on field. And that can be explained by the rate limiting steps that we see on these. So on the strong binding side, we're limited by the coverage of OH, which, if we remember, that OH had a much stronger or a much weaker field effect than some of the other adsorbates we looked at. And on the right-hand side, we're limited by the first protonation of O2 to OOH. And this has a much stronger field effect than this OH coverage. So what do we learn from this? We learn that these gold catalysts have this large pH dependencies because they have a different rate limiting step than platinum 111. Further, this kind of means that we would generally expect weak binding catalysts, not just gold catalysts, to perform better in in base than they do in acid. Okay, and now we can look at the 2-electron ORR behavior to try to understand that kind of strange phenomenon we saw on gold 100, where it was going from having the same onset potential as the 4-electron ORR to having a different onset potential. So once again, I've plotted the activity volcano of the hydrogen peroxide, the 2-electron ORR at 0.6 volts here. And I've placed the three different catalysts on the volcano. And what we can notice here is on the strong binding side, we're limited by the second protonation, OOH to hydrogen peroxide. And on the weak binding side, importantly, we're limited by the first protonation, O2 to OOH, which, if you can remember from the last slide, is the same rate limiting step as we see in the 4-electron ORR. And so if we look specifically at the two gold surfaces, first at gold 111, what we see is that the activity increases when you go from acid to base, but you stay on this same weak binding side of the volcano where you're limited by the same thing that the 4-electron ORR is limited by. However, the gold 100, as you go from acid to base, switches from the weak binding side of the volcano, where it would have the same behavior as the 4-electron ORR, to the strong binding side of the volcano, where it would have different behavior. And so what we see is that these weak binding catalysts, which have the same rate limiting step for the 2-electron and 4-electron ORR, lead to the same behavior or the same onset potential for the 2-electron and 4-electron ORR, as happens in gold 111 and in gold 100 in acid. Also, we can kind of notice that this kind of strange behavior that's been reported many times on gold 100 can be explained not by anything weird that happens on gold 100, but rather just based on where it lies, how strong of a binding catalyst it is, kind of in this mid-range strength binding catalyst. So with all of that, I hope I just leave you with a few conclusions. The first is that for the 4-electron ORR, the reason we see this large pH dependencies on weak binding catalysts is because they have a different rate limiting step, specifically that they're limited by OOH and O2, unlike strong binding catalysts like platinum, and that we expect this phenomenon to be true in general on weak binding catalysts, that they would perform better in base than in acid. Second, that the differing 2-electron and 4-electron ORR pH dependence on gold 100 can be changed in explained by changing from having the same limiting step as 4-electron ORR and having a different limiting step between the two different reactions. And finally, and I really think this is the most important thing, is all of these observed phenomena that we look at on different catalysts reflect similar effects acting on different catalysts. They're not a bunch of different strange phenomena. They're really one phenomenon affecting catalysts that have different binding strengths. So with all that in mind, I hope you enjoyed this talk. I really skimmed over a lot of the methods. So if you're interested, I will have a link to the paper where we go into a lot more detail. And that will be in my iPoster. So thank you, and I'll be available for questions.